So, good morning everyone and welcome to the second session on probabilistic planning. So our first speaker is Cyrus, actually, not Jean, but Cyrus, and online risk-bounded motion planning for autonomous vehicles in dynamic environments. Apparently the mic of the speaker does not work.
Hello? Test. Okay,
Thanks.
great. All right, good morning, everyone. So my name is Cyrus, and I'm the first author of this paper called Online Responded Motion Planning for Autonomous Vehicles in Dynamic Environments. This is a joint work between Sungkweon Huang, Andreas Hofmann, and Brian Williams at MIT CSL. So I want to begin with a few motivating examples on why it is important and challenging to do responded motion planning in dynamic environments. So from this video, you can see that driving can be a very dangerous event because of the unexpected behaviors from the other drivers on the road. So, so for some of those who went to industry panels, you might already seen a lot of those videos, but the key takeaway is that many of the crashes happen at intersections. So according to a study from US Department of Transportation, about 40% of those crashes happen at intersections and related areas, and most of those are due to false assumption of others' actions or misjudgment of the gaps. So in this work, we claim that to avoid those crashes, it is important to recognize intentions of the other agents in the environment. So in this specific scenario, let's say we have an ego vehicle that we want to control in yellow that wants to make an unprotected left turn. And there's an upcoming red vehicle that can either choose to slow down or just go forward. So in order to make a safe and efficient left turn, we claim that it's important to recognize that intention. So in this example, the ego vehicle recognized that the red vehicle is going to slow down, so the planner would just ask the ego vehicle to turn immediately. So this is a very simple starting point. And next, I want to introduce how the problem in our work is actually formulated. So in this work, we assume that we can control a single autonomous agent that is in yellow. And it has to navigate safely and efficiently in a dynamic environment that with a bunch of other agent cars, for example, this one in red. So we assume that we can observe the states of those cars, and the output of our online decision-making system is an optimal action that the ego vehicle can take. So more formally, the inputs include a set of observed environmental states, such as the agent vehicle's positions, and a set of available actions that the ego vehicle can choose from, and their associated costs. We also assume that we know the goal state in advance where the ego car is going to. And because we care about safety and risk, so we also have a set of risk constraints that the ego vehicle should not violate, such as not colliding with the other vehicles. The output is an optimal, safe, and deterministic action for the ego vehicle. So if you think so this is natural to think in the MDP or POMDP domain. So in this case, we model our problem as a chance-constrained, partially observable Markov decision process, which comes from an existing literature from 2016 from Santana. So this is, the tuple includes the following items. So first, it has a set of discrete hybrid states, including the discrete maneuver states and the continuous positions for each vehicle in the environment, including the ego vehicle and a bunch of other agent vehicles. Also, we have a set of maneuver actions that can be taken by the ego car. The rest is the standard POMDP elements, including observation sets, transition function, observation function, cost function, initial belief state, and the final planning horizon. The difference between standard POMDP and chance-constrained POMDP is that we introduce an upper bound probability for the risk constraints. The goal for this problem is to find a responded optimal policy that can help the ego vehicle to navigate the goal as soon as possible without colliding with any of the other agent vehicles. So compared to a lot of existing literature which deals with such kind of problem, they usually assume a fixed or static transition function, which means they assume that the agent cars in the environment, they will always move by the same pattern, which is not true because of the intentions of the agents can change over time. So in this work, we focus on updating the transition function in real time in order to achieve safe planning. So now let's dive into our methods, starting with the architecture diagram. So in this work, we propose an online decision-making system with the 3 components. So the first component is an offline maneuver model generator that takes a set of demonstrating trajectories and generates a library of probabilistic maneuver motion models. Given this library, we can use it in our intent recognition system that observes a set of trajectories from the agent cars and updates the intentions over each of the agent vehicle. Finally, we have our responded conditional planner that takes the intentions and update the transition function before it computes the optimal policy for the ego vehicle. So in the rest of this part, I will go through each component with more details. So first, let's start with the maneuver model generator. The idea behind this is very straightforward. So for each maneuver, we assume we can have access to a set of demonstrating trajectories, and we want to learn a probabilistic maneuver model for each maneuver. So in this, so as we model this as the probabilistic flow tubes proposed by Don in 2012. So in this specific example, let's say we can generate our trajectories from a vehicle simulator where we use Keller in this case, and we drive the vehicle to make a right turn for a bunch of times and collect the demonstrating trajectories. And given those trajectories, we can compute a PFT that includes a nominal trajectory and a sequence of covariances that model the uncertainties of the motions along the trajectory. So this is a very compact but powerful representation because it models the realistic human behaviors for each maneuver. So after we learn this library of probabilistic flow tubes, we can use that for our online intent recognition system. So the goal for this component is to estimate the hybrid states, including the maneuvers and the positions for each agent. We model this as a hybrid estimation problem, where we first estimate the current discrete maneuver states using the probabilistic flow tubes and Bayesian filtering. So we get the observations from the PFTs and the observations and use the prior to update the distribution over the discrete maneuver state. And once we know the current maneuver state, we can predict the future hybrid states by first predicting the next maneuver state using a pre-learned discrete transition function and the current distribution over the maneuver states. And because the PFT models the continuous evolution for each maneuver, once we know what maneuver it is, we can predict the future continuous positions given the information of the PFT and the predictions over the discrete maneuver states. So after we recognize the intentions, we have to feed it into our MDP instance. So as a reminder, we modeled this online decision-making problem as a trans-constrained MDP. So we use a state-of-the-art solver to give us the policy using heuristic forward search. So the solver's name is called responded AO star, and it utilizes 2 different heuristics. The first one is a utility heuristic that helps us to guide the search towards optimal policy. And secondly, we use a risk heuristic that can help us to prune the over-risky branches to speed up the search and ensure the respondent's outputs. So a key change in our work is that we update the transition function in real time using the intent recognition results that we updated earlier. So because of the time constraint of this talk, I'm not going to many details with the solver, but this is a very simple idea of how it works. So in this case, let's say we have a lane change scenario where we want to control the ego vehicle that can choose from a set of 3 actions whether to make a lane change to the right or go forward with 2 different speed profiles. And on the other hand, we have an agent vehicle that can go forward or make a lane change to the left. So the goal of the ego vehicle is to move to the go region as soon as possible without colliding with the agent car. So this is how the search will look like for a planning horizon of 1. So in this case, we would prune the action of the ego vehicle to make a lane change to the right, because the risk of 0.5 it exceeds the respawn of 0.1 that we specify. So we can just prune that part of the branch and save the search speed. And we also utilize our second heuristic to guide our search towards more optimal areas. So in this case, because going forward will help us lead to the goal region faster than going slow down, so we will decide to search towards that region instead. So so far I have introduced 3 components of our approach, and now let's see how it works. So I want to start with an unprotected left turn scenario that I just introduced. So again, in this case, we have our ego autonomous vehicle that we want to control in yellow, and the goal of this vehicle is to make an unprotected left turn as soon as possible without colliding with the other upcoming red agent car. So we are using Keller again in this demo, which is a realistic 3D vehicle simulator. So in this case, after the ego vehicle will recognize that the agent car slows down, so we just turn immediately because it sees no risk. And in this demo, the ego vehicle will predict that the vehicle will not yield to it, it will just go forward, so it would decide to wait for a bit and then make the left turn. So a very interesting thing we find in this paper is that we can actually tune the upper bound on the risk to simulate different behaviors of the ego car. For instance, we can increase the delta, the respawn, to give it more to have higher risk tolerance. In this case, after we increase the risk tolerance, it will just turn faster because it still thinks it's kind of safe to turn because it predicts the future positions of the agent car. But and it doesn't have to wait all the way after the agent car to pass intersection to make the left turn. So in this case, we simulate kind of a more aggressive behavior for the ego vehicle. Another demo I want to show is the lane change that usually happen at highways or a lot of other dynamic driving environments. So again, in this case, we are controlling our ego vehicle that wants to get to the destination as soon as possible without colliding with a bunch of agent cars in these environments. So here we model 3 agent cars that can either go forward or make a lane change. So in this example, we have designed that the ego car is moving faster than the agent car to encourage it to bypass it when it's safe. So at the beginning, you will see that the ego car will start to make a lane change to bypass the 2 slow vehicles. And but because the gap to make a right lane change is small, and we have a very small response, so it decides to follow this red vehicle because that's what is safe to do. Again, I can increase that response to simulate a more aggressive behavior where we give it more higher risk tolerance so that it can just make the lane change. So it looks scary, but this is what we get the trade-off between the efficiency and safety. Again, we also demonstrate the online capability of our system because it can recognize intentions of the other vehicles in real time and update its plans. So in this case, it recognized that this red vehicle is going to make a lane change, so we'll just decide to slow down and make a lane change to pass those slow vehicles. So those are some qualitative examples, and now let's take a look at some quantitative numbers. So in our study, we compare our planner with 3 baselines in the left turn scenario, unprotected left turn scenario. So on the top half of the table, we show some numbers with 3 baseline models. In the first baseline model, we have a very conservative planner that assumes the agent car is always going to go forward. So it will control the ego car to wait and then make a left turn before the red car passes. So it guarantees 100% of success rate, but on the other hand, the efficiency is bad because it has to wait no matter what the agent car is going to do. On the other hand, we have a risky planner that assumes that the agent car is always going to slow down and wait for us. So this is another extreme of the spectrum where the car will just turn, but the success rate is only over 50%. We also test with another planner that uses a physics-based motion predictor that uses the velocity, the acceleration of the agent car to generate the future trajectories of the vehicle. So in this case, it yields the higher success rate than the risky planner, but it's still not as satisfiable as we would expect. So on the other hand, our planner that can achieve 100% of success rate, but keeping the completion time lower than the conservative planner. So on the bottom half of the table, we also test our planner against the same baselines on the lane change scenario. So we can see that our planner can guarantee the success rates by respecting the risk bound while having a very good completion time. So we try with different upper risk bounds in this study. So we can see that when we increase the risk bound, we see the expect behavior that the success rate actually decreases, but they still respect our the upper bound on the risk. And on the other hand, the completion time is getting better. So here we see, again, a trade-off between safety and efficiency. So we also, so as many of the audience may already know that the MDP is hard to solve if we have a very large problem size. So in this case, we actually study the time complexity of our algorithm. So we try to change the planning horizon, and as well as the number of agents which affect the branching factor in the search from various numbers. So in this case, we can see that in order to guarantee a planning time of 200 milliseconds and to deal with 3 agent vehicles, we have to reduce the planning horizon to 2. So this is not ideal, but because of the online capability of our planners, so we can always replan even though the planning horizon is small. Again, also we think the number of 3 agent vehicles is good enough for most of the cases in the traffic because the vehicle usually only deals with at most 3 vehicles. So in conclusion, we have developed a system that recognizes the intentions of the other dynamic agents quickly and efficiently. So our system is able to produce responded policy for the ego vehicle in a dynamic environment that drives with a bunch of other moving vehicles with stochastic intentions. We simulate different driving styles from our planner that's based by tuning the different upper bounds on the risk constraints. Finally, we demonstrate our system in 2 very safe critical scenarios in a very realistic vehicle simulator, one in the unprotected left turn and another in the lane change scenario. So some of the future work includes adding more features to the maneuver model so that it can become more robust. And also we want to improve the efficiency of our planner in the future so that I can handle more agents and longer planning horizons. So thanks for listening, and I'm open to any questions. Thanks.
Thank you. Any question? Yeah.
So the risk bound you're willing to take, that's for the horizon, right?
Yeah.
Which is very short.
Yeah.
So that means that if you're taking a risk of 0.1% for, let's say, a 5-second maneuver, right, then you will crash every 5,000 seconds, which is maybe less than ideal.
Well, so because we are planning in the maneuver domain, so let's say each maneuver has 5 seconds, so like a planning horizon of 2 would be like 10 seconds into the future.
Okay.
Yeah. Also, yeah, we are working on. We have a paper at ICAPS this year trying to improve the efficiency of our planners. It can actually take more longer horizons in the future.
Yeah, nice talk. So one of the things that we see is all of these unknown unknowns that can occur. We've seen lots of videos. Yep. And so your probabilistic model is learned under the assumption that you know everything that could possibly happen.
Yep.
So maybe you could just talk a little bit about how you see maybe that's not an issue, like eventually you'll be able to recover from that, or what needs to be added to your algorithm to cover these unknown unknowns?
Yeah, that's a very great question. So in this case, that's the reason why we model the behavior with uncertainties. That's a way to consider the different human actions. In this case, we are modeling the maneuvers because it allows us to predict longer. So in a lot of the other works, they are planning for like shorter horizons that they consider different features of the environment, such as the distance to the leading vehicle, the distance to the lane center. So those allows us to have a more comprehensive model that can be used to make future predictions. So it's a trade-off between the predicting horizon. So if you want to predict longer, then you have to add some structure to your predictor. So here, I think our best bet is that by modeling it as a probabilistic model, so we can handle some of those uncertainties.
One last question, very short, please.
Nice talk, thank you. Do you take into account that what other agents are doing will be affected by the decisions that the self-driving car takes? Yeah. So for example, if you merge, the other agent will slow down. And if not, can you incorporate that in your model?
That's a very good question. So for the prediction parts, we don't. So we assume that each agent, they will just behave independently. So that's not a very robust prediction, I admit. But in the planning part, we can actually eliminate some of those like unrealistic predictions, because in the lane change scenario, if we plan the two vehicles will go to the same place, we know that that's not possible, even that our predictor tells us the vehicle is going to make a lane change in front of us. So we can eliminate some of those predictions in the planning side by checking the tree, how the tree progress. So that's a way to take account of those kind of interactions. But I think for the planning part, we have not yet considered the interactions yet. But that's another future work direction. Thanks.
Okay, thank you. So we are running out of time, so I'm sorry. You can speak with the speaker after this break. Thanks. So the next speaker is Rui. He will speak about a theoretical and algorithmic analysis of configurable MDPs.
Okay, hi everyone, thank you for coming. My name is Rui Silva, and today I'll be presenting a joint work with Gabriele Farina, Melo and Manuela Veloso. And in this work, we make some theoretical, algorithmical, but also some practical contributions to configurable Markov decision processes, or MDPs for short. This is a very recently introduced model, and for those that attended the goal recognition session, you'll see that they are somewhat related with the equi-reward utility maximizing design model that Sarah Karen introduced yesterday. But anyway, let me start by briefly motivating configurable MDPs. And let's assume we have a service robot like that does not have arms, and the goal of our robot is to deliver a package to a human user in the fastest way possible. And it just so happens that the robot and the user are located on opposite sides of a long corridor like this one. Now the robot performs some planning and determines the best plan to execute. And because of those black obstacles there in the middle, separating the corridor, the robot determines that the best plan is to traverse the entire corridor like this. So go all the way to the right, move down, then go all the way to the left. But even though this is the best plan, and effectively, in this case, the fastest way of performing the task, it may still take a long time. The corridor may be very long, and the robot may be very slow. But more importantly, it's important that we understand that we agree this was the best plan, because implicitly, we made the assumption that those obstacles there are fixed. We implicitly assumed that they were static. However, let's now assume that these obstacles are not static, and that instead, they actually correspond to those brown doors that just happen to be closed. Now, our robot does not have arms, so it cannot open the doors, but we do know that doors can be opened. Not by a robot, but they can still be opened. And opening and closing different doors leads to what we call different configurations of the world. So we may have the world with all the doors closed, the world with all the doors open, Some doors may be open, some doors may be closed, and different doors may be opened at different angles. So we have this continuous set of possible configurations of the world. But going back to the original configuration with all the doors closed, again, in this case, the best plan is still to traverse the entire corridor because our robot does not have arms it can use to open the door. However, there may exist other configurations that may be more advantageous, even if we assume a potential cost for getting such configurations. So for example, the human user may actually be willing to open a door for the robot if that resulted in an advantage to him, meaning getting the package sooner. And in fact, if somehow the human user or some other external entity were to open the first door, the robot would then be operating in this different configuration of the world that allows for this much shorter plan. And it should be clear that this is better. So that example illustrates the key idea behind configurable MDPs, and that is we want to plan and reason over these additional possible configurations of the world that are not necessarily reachable through the execution of the actions of the agent. And the goal is to identify the configuration where the performance of the optimal policy is maximized. And so in a sense, we're here playing around and exploring this connection between configurations of the world and the optimal policies induced by such configurations. So more formally, a standard MDP is described by this tuple. We all know it: state space X, action space A, reward function, discount factor, and an initial state distribution. But more importantly, we have P, the probability transition function that describes the transition dynamics of the world, meaning how does the state change as a result of the actions of the agent. And the goal here is to compute the optimal policy under a fixed world configuration. Whereas in configurable Markov decision processes, we have some additional terms. So we have P0, which we denote as the initial configuration. So in our corridor scenario, this would be the world where the robot started, with all the doors closed. We have this set calligraphic P that we denote, that we use to denote the set of possible configurations of the world. So in our corridor scenario, that would be the set with the configuration with all the doors closed, all the doors open, and so on. And finally, we have the cost function C that measures the cost associated with shifting from P0 to a new world configuration. And so the goal, again, is that of computing that optimal world configuration P star that maximizes a given benefit cost trade-off. That can be modeled with this optimization. So we're maximizing that objective function over the space of possible world configurations, calligraphic P. And the first component of this objective function measures the best possible performance of the agent in a given world P. So more formally, this is the expected sum of discounted rewards of the agent in a world by following the optimal policy there. And the second term is, again, the cost for shifting from P0 to a new world configuration. Okay, so in this work, the first question we asked was, how hard is it to solve that optimization problem? How hard is it to solve a configurable MDP? And we contributed an analysis on the complexity of this problem. So we showed the optimization problem is non-convex and that the decision problem associated with such optimization is actually NP-hard. So we reduced the 3-set CNF problem to a configurable MDP. I will not go through all the details. You can find them in the paper. But essentially, we start from an instance of a 3CNF formula like that. So we have conjunctions of these junctions of 3 Boolean literals. And given an instance of a 3CNF formula, we create an instance of a configurable MDP. And now the interesting part is that we establish a mapping between the transition probabilities, which are configurable, and the assignments to the Boolean variables of the 3CNF formula. And we do this in such a way so that the optimal configured transition probabilities allow us to extract assignments to those Boolean variables that satisfy the formula, that make it true. And it's well known that computing an assignment of Boolean variables that makes a 3CNF formula true is NP-hard, and so solving our configurable MDPs is also NP-hard. So given that, we probably should not expect a very efficient and optimal algorithm for solving the general case of configurable MDPs, and maybe approximated algorithms are a good way to go. And on that note, we considered a gradient-based approach for solving these configurable MDPs. We considered this algorithm we had proposed previously under the name of p-iteration. And the way it works is as follows. Let's assume we have this arbitrary surface of the objective function in terms of possible configurations of the world. So this is just an arbitrary example. And what we do is we sample a possible configuration of the world P0, and then we iteratively build a sequence of world configurations that converge to a local maximum of our objective function. And we do this by following a standard gradient update rule. Now, because the problem is non-convex, we essentially repeat this procedure a couple of times, starting from different initial configurations and hopefully reaching different local maxima, so that in the end we can return the best solution we find. Now, computing that gradient of the best possible performance in a given world is kind of tricky because we have some non-differentiable dependencies. Namely, note that best possible expected sum of discounted rewards depends not only on the world, but also on the optimal policy in that world. And unfortunately, the computation of this optimal policy has that non-differentiable dependency on the world configuration itself, because we have that argmax operator. So in previous work, we introduced a method for somewhat estimating this gradient. And what we did was very simple. What we did was, at any time step k, and for a given world configuration pk, we start by computing the policy. But then, when we are computing the gradient and going backwards, we fix that policy and we ignore that dependency. So that's why you see it in grayed out. So in practice, what we were doing was we were ignoring the fact that when you change the configuration of the world, the optimal policy may actually change. So again, previously we had introduced this as an approximation. But in this work, we formally derived a gradient method for computing this gradient. We followed the Karush-Kantuker conditions. You can find all the details on the paper. But more interesting is the fact that by deriving this method, we were able to understand that this other method we had proposed previously is actually computing the exact gradient, except in a small number of points. And the key insight is that it turns out that in most circumstances, for small perturbations of the world, the optimal policy actually remains unchanged. And so most of the time, this is OK to do. So the final contribution is from a more practical perspective on configurable MDPs. And we analyze different ways of specifying that set of possible configurations of the world. And essentially what we do is we assume that the world is somehow parameterized by some parameters, and different values to these parameters allow for different configurations of the world. And since in configurable MDPs, we assume that world configurations are described by transition probabilities, essentially what we're doing is we're parameterizing these transition probabilities somehow. So we started by considering what we called these local parameterizations. And in these local parameterizations, we let each parameter configure very specific and targeted entries of the transition probabilities. So for example, that red parameter is only configuring those 2 entries in the first row. The blue parameter only configures those other 2 entries in the third row, and so on. So very target and very specific. And an example of this in practice, in our corridor scenario, let's say we want to configure the openness of the first door that is blocking the passage between state 1 and 4. What we would do is we would create a parameter theta 1 that represents the openness of the first door. So when theta 1 is equal to 0, we would say the door is closed. When theta 1 is equal to 1, we would say the door is open. And then we parameterize the transition probabilities in that way so that we are able of configuring the probability of the robot moving down when in state 1 with that parameter theta 1. And if we want to configure the openness of the second door, we would create a new parameter theta 2 that would now configure the probability of the robot moving down from state 2 to 5. So we then considered what we called global parameterizations. And here what we do is a bit different. We assume that we can specify some vertex world configurations. So let's say P1, P2, P3. And then we further assume that a possible configuration of the world must lie in the space of the convex combination of these vertex configurations of the world. So an example in our corridor scenario would be like this. So we would start by specifying the configuration with all the doors closed, configuration with all the doors open, and then the configurations with only the first door and then only the second door opened. We would then associate parameters with each one of these, and we would do the optimization and the gradient algorithm over those parameters. So, important thing to keep in mind is that these global parameterizations are a nice way of modeling these changes to the world that affect multiple entries of the transition probabilities at the same time. This is not really visible in this example, but in the paper you can find a much more elaborate scenario where this becomes more clear. But also note that we still had the same two changes to the world, which were opening the first and the second door, but these required 4 parameters. So the key message is that for different problems, we have a choice to make, maybe between those local or these global parameterizations, and they have advantages and disadvantages. So as a takeaway message, in this work, we contributed a theoretical analysis on this recent model of configurable MDPs, where we showed it's actually hard to solve the general case. We also have some algorithmic contributions here, where we propose a gradient-based algorithm for solving them and show its correctness. And in the end, we also analyze this model from a more practical perspective and discuss the pros and cons of some different ways of specifying that set of possible configurations of the world. Thank you very much. Let me know if you have questions.
Thank you, very interesting. So I wanted to clarify, when you're talking about complexity, right, then the representation size matters. So are you talking about a flat representation of the states and of all the possible configurations, or is there some compact representation somewhere?
What do you mean by flat representation?
Is it in the number of states and the number of possible configurations, or in some size of a factor description? So of a representation system of state variables.
I would say it's in the size of the state space. I'm not sure I fully understand the question, but I would say it's on the size of the size of the state space. Yeah.
All right. So I think the more interesting part is how you describe the possible configurations. Do you just have a list of all possible configurations, or?
Oh, in that case, we use a parameter similar to that local parameterization that we used. So the transition probabilities are represented by parameter theta, and the opposite is 1 minus theta. Yeah.
For each possible transition probability?
Sure.
Okay, thanks.
So if I understand correctly, you are formulating an optimization problem on a continuous, like the polytope of possible transition distribution functions. But your set of configurables, your set of possible, this is quite a combinatorial structure. So can you say something about gradient descent applied to that type of optimization?
Yeah, that's a good question. And that's why we explore this idea of parameterization, so that we can somehow control the space of the search, because otherwise it's too large to find anything reasonable. But we found out empirically in previous work, and a little bit in this one, that by having these parameterizations, you can somehow control the space of the search and be able to get some interesting results. I don't know if that answered your question.
Thanks for the talk. Can you further explain why can't you encode this model into regular MDP? For example, encoding the configurations in the states, and the actions will encode transitioning between configurations, because you're already using discrete parameters for configurations. And this will also allow you to transform between configurations during the execution itself and not only initially.
That's a very good question. I would say there's nothing particularly wrong with following that approach. But keep in mind that here we are considering that you can actually have continuous modifications to the transition probabilities. And so if you want to go that route, you'd probably need to have an action for each possible change in the world. So you would probably need continuous actions, and probably you would also need continuous state space. And solving a continuous state and action space MDP is also not that easy. So it's not clear to me that approach would be better than this. But even from a more conceptual point of view, I would say that by using that, you're kind of saying that the robot or the agent is the one that is able of executing those changes to the world, which I don't see as the case. So we see that the environment is modifiable. So it's not the agent really that is modifying the world. But,
I think to clarify the question,
okay.
The idea, actually you transform your original program into a regular hybrid MDPs with hybrid states, but then at execution, you only keep the agent won't execute the configuration changes.
Mm-hmm.
So it's just a way to transform the original problem into a hybrid MDPs, but then the agent only executes its own action.
Okay, it's actually a good idea. Maybe we should discuss a bit more offline. Thank you.
Okay, yeah, I have a generic question.
Okay.
So in many configuration generation problems, for instance, transportation systems,
Mm-hmm.
you want to optimize one configuration not for a single agent, but for many different agents.
Mm-hmm.
So I am wondering which kind of real application you target here, and if you have thought about, for instance, generalizing it to multi-objective optimization, or at least averaging over many possible agents.
We haven't considered that. That's actually a very interesting idea. In terms of scenarios, we've been considering mostly grid-based scenarios so far, but that would be an interesting way to go from here. Yeah.
Thanks. Any other question? Yeah. We still have 1 minute, so that's fine.
The gradient method you described is similar to the continuous space technique of linearizing a system around a neighborhood, for a neighborhood around a fixed point.
Okay.
And then when you use that gradient, if you use it outside of the neighborhood, you relinearize in a continuous space.
Okay.
So I think in this case it would be like, did you look into how many perturbations of the model you make before you need to recompute the optimal plan?
We haven't done that statistic, but that's actually an interesting thing to explore for sure. But no, we haven't done that. But good idea. Thank you.
So let's thank the speaker again. So the last talk of the session will be done by Huang on stochastic planning with lifted symbolic trajectory optimization.
Okay, good morning, guys. My name is Hao. So I'm here to present this paper, Stochastic Planning with Lifted Symbolic Trajectory Optimization. And this paper is co-authored by with Thomas Keller and my advisor, Roni Khardon. So in this paper, we're presenting a MDP planning algorithm, and it's online planning algorithm. And although the recent kind of dominating online planning algorithm have been the real-time dynamic programming and the UCT-based algorithms, our work is taking a very different approach, a very different direction. It's very simple to understand, and it has excellent performance on the IPC challenge problems. Actually, we outperformed the winner of the IPC this year with a significant margin. So it's very simple to understand, but here's what I'm going to talk about. I'll start with the problem setup, the problems that we work on, and then the motivation for the so-called aggregate simulation, which is the core idea of our planning algorithm. And then I'll go into the details of aggregate simulation And so both is our planning algorithm and then the experimental results. So the problem setup is very simple. So we work on the discrete probabilistic MDPs with hard action constraints. And we emphasize constraints here because constraints are very important to modeling the real problems. For example, if we have two robots operating in the same room, we have to make sure they don't run into each other, right? So such constraints, we support that in the planning. And also the online planning, which focuses on finding the action with the highest Q value. And we work on binary domains, but possible extensions to continuous domains and non-binary discrete domains is possible. If we have time, we'll talk about that later in the end. Okay, so I'll start with a very simple rollout algorithm. It motivates our idea. So I'm sure you are all familiar with this. So it's very simple. It searches over all the actions and returns the action with highest Q estimate. And where the Q estimate is performed by simulating many trajectories and averaging over the sampling results. Okay? And the rollout algorithm requires a so-called rollout policy, which is baseline, and is guaranteed to improve over such a policy. That is the setup of a rollout algorithm. It's very simple, but actually the tree versions of it, like multicolor tree search and UCT, are very powerful and popular, especially in the field of game playing. Like the AlphaGo is actually using UCT as its main planning algorithm. The main difference between the MCDS and the rollout algorithm is that these algorithms are optimal. And if it can have time to fully expand the tree, then it's optimal. That's the kind of the condition that it has. Okay? And we observe several limitations of rollout algorithms and potentially also for MCDS. What are those? And we're particularly looking at the large problems, and especially the problem with large action spaces. So the first difficulty for rollout algorithm is that the average budgeting time for each of the action is very small. It can be very short if the action space is large. And then the sampling itself is unreliable because it has a high variance, and the Q estimates can be unreliable. The second difficulty is that even if we can get a good estimate of the Q values, it is still hard to search over such large action space. And the third problem is that the quality of the rollout algorithm actually depends on the quality of the rollout policy. But how can we find a good rollout policy for any domains, especially in terms of talking about build a domain-independent planner? And one might argue that MCDS problems don't have the MCDS algorithm don't have this third problem because it's optimal. But actually, in reality, is that with a problem with very large action space, it's very hard to fully expand the tree. And we often observe, actually, it goes to one extreme, which is the MCDS downgrades to just a rollout algorithm, so which have the same problem as the rollout. I promise that our approach is trying to solve these problems, three problems at the same time, through the core idea called aggregate simulation. And we'll start with the motivation of it. So the left of the slide is just the rollout process. And we don't like the sampling. It can be expensive and it has high variance. What about we do this? Supposing that we can directly calculate the probability distribution of the states and actions in the trajectories. And we do it for all the steps. If we can do that, then we can calculate the expectation of the reward function, also for each of the steps. And for sure, we can calculate the immediate reward of the first step. Together, we can directly calculate the Q value. But everything starts with calculating the probability distribution of the states, which is very hard. It's basically infeasible. So we need approximations. And the approximation that we're doing here is probably the simplest, is just we work with the marginal probability of the state and action variables, assuming independence. We will discuss different assumptions, possibility of supporting different assumptions in the end if we have time. But for now, we'll just keep it as simple as it is. And now we're talking about, can we calculate the marginal probabilities of the state and action variables in the trajectories? And here's how we calculate it. Let's directly look at the two equations. The first equation is we estimate the P of x, where x is the state variable, as this big sum, where inside of the sum is just a joint probability of the variable x and a certain assignment of its parent variables, which is denoted as Cij here. So what it says is that, okay, let's just sum over all the possible assignments of the parents, and inside of the sum, it's a joint probability of the parents and the variable. It's very simple, chain rule and marginalization. And then the probability of Cij is approximated by assuming the parent variables are independent. So it's just represented by the marginal probabilities of it. Together, it gives us the two equations that we can calculate the P of x as a function of the marginal probabilities of its parent variables in the transitions. Okay? Those are very simple, but together we can directly calculate the Q value. How to do that? So let's assume that we only have 3 steps of search. And let's start with the dBn representation of the factor model. And apparently the first step, the state and action are observed because that's the Q value that we're estimating over. And we know the marginals there. It's either 0 or 1s. And we can directly calculate the marginals at step 2. And note that the marginal probability of A1 prime, which is the action, the rollout action variables, the marginal can be easily calculated, assuming that we roll out random policy. We'll deal with the random policy later, but here we're just assuming we're rolling out random. And together, let's add the reward function, and as explained, we can calculate the expectation of the reward. Let's concatenate one more steps and get marginals and expectation. Together, we calculate the Q. So it's done in a forward manner, in an algebraic way, to calculate the Q value. Okay? And we have proved in our previous paper that the Q value computed by aggregate simulation is actually equivalent to performing a belief propagation algorithm, which is approximate Bayesian inference algorithm over the corresponding graphic models, like in here. Okay, so it's equivalent to BP, and this is a nice property to have in the sense that this provides us a tool to analyze and understand our algorithm and improve it. And now we come to the main algorithm named SOBOFA. So what we have talked about so far is that the aggregate simulation provides an efficient estimate of the Q value, although it's approximate. But it's still difficult to search over large action space given that aggregate simulation. And what we are going to do is, for the SOBOFA, let's recap the graphic model that we have mentioned about in previous slide. We said that we can estimate the Q value of a given action, where the color nodes here is say this variable is observed. What if we don't say it's observed, but keep it as keep the marginal probability of this action variable as a parameter? And in that sense, if we still do the forward calculation, we can imagine that the Q value, the Q is not a value but a function. It's a function of the marginal probabilities of initial action variables. Such a function can be such a function can be captured by a computational graph where inside of the computational graph, each of the nodes is either a mathematical operation or a marginal of the action variables. So the SOBOFA algorithm goes like this. The first step is that we build the computational graph with dynamic depths. What we mean by dynamic is that here the K is decided in the graph construction time. It's dependent on the problem that we work on, the hardware, and the budgeting time for planning. And it's like any other optimization problem. If we have time, we can perform a random initialization for the marginals of the action variables, followed by multiple gradient updates. So we're actually optimizing the Q value with respect to the marginal probability of the action variables. So let's assume that once we make the gradient updates, we get 0.2, 0.8, and 0.1 for the initial action variables. We can sample concrete action out of it. Let's say it's 0, 1, 0 here. And we plug in, we evaluate the concrete action using the same Q graph. We don't evaluate the marginal probabilities, but we evaluate the sampled concrete actions. And then we record the best. We loop the steps 3 to 5 until convergence, and if we still have more time, we do another random initialization. So this whole algorithm can be seen as a mix of a continuous optimization problem and a discrete search problem. The difference is that if you do a normal discrete search, you always do it with a uniform distribution of the action space. But here, the search is guided by the marginal probability of the action variables, where it's updated according to the gradient ascent direction of the Q function. So this is the whole algorithm of SOBOFA. And in our previous results, we have shown that SOBOFA performs amazingly well for and compared to the only using the aggregate simulation or compared to normal MCTS and rollout algorithm in the big problems. But the main contribution of this particular ICAPS paper are two powerful extensions that is called lifted and conformant. So together, it has become a very powerful planning tool, and we start supporting the hard action constraint inside of the graph. So I'll explain each one of them. I'll start with the lifted construction. So the idea is actually motivated by the lifted BP algorithm in the Bayesian inference literatures. And what it says is that actually, let's look at the left of the slide. It's just a naive construction of Sungkweon. While on the right-hand side, we're doing the lifted construction, where if we know that is a node, there is a node that has the same mass operation and the same children with another node that's already inside of the graph, then we should directly refer to it, not creating a new node. It's very simple, but we designed a way to implement it in a dynamic programming way, so the additional computational cost for building the lifted construction is negligible. But it brings in a magnificent graph size reduction for many problems. Even for this small example, we can visibly see the graph size reduction. And with a smaller graph, we're hoping more efficient gradient updates and hopefully better performance. And eventually, I want to talk about the conformant extension, where this problem is particularly designed, the extension is particularly designed to roll out a non-random policy, which is important to many problems. As we have mentioned, actually, rollout problem for a lot of people, it's just rolling out random. It's not working for many problems. But for the MCDS, it also has similar problems. The action space is large. So here, we're trying to optimize a non-random rollout policy for any problem. We have many analyses of why we do this, why we not do that, but I'll skip the details but directly go to the results. What we're doing here is very simple. It's that inside of the circle, we are treating the marginal probabilities of the rollout action variables also as parameters, not a constant out of the random policy. So the idea is simple, and the resulting Q function just has more parameters to optimize. It becomes more complicated optimization problem, but after optimization, the optimized marginal probability of the rollout action variables can be seen as a projection of a non-random rollout policy. And we'll show in the results that this is very important for many problems. Okay? And we're also handling hard action constraints. Especially for this 4 types of, which covers a lot of different constraints. The first one is the action implies a condition. So for example, we can say, if you want to take this action variable to be true, then you have to satisfy another condition, which, say, is a union of 2 state variables, or whatever condition. And the second one is so-called concurrency constraints, where you have the sum over your action constraints to be true. It should be smaller or equal to a constant. The third one is a condition, is that if condition is satisfied, it implies that I have to take one single action variable or a set of action variables. Or we have to satisfy that the set of action variables, that is, the sum of the action variables being true, has to be greater than some constant. And the fourth type is just an empty condition for that. So it's forcing some action to be taken. These are just 4 major types, but it actually covers a lot of different constraints that we can use. Most importantly, I'm skipping the details of how to handle this, but most importantly, we handle this constraint inside of the graph. What it means is that during any step, during any time of the gradient updates and the action search, the action that we evaluated are guaranteed to be legal. So without any rejection or sampling or this kind of a legacy check. Okay, that's what we do for this paper. And I'm going to the results. The Sungkweon, we compared the Sungkweon to the winner of IPC 11 and 14 and 18 PROS, which is a UCT-based algorithm. It has been a very powerful planning algorithm in the recent years. And what I'm saying is that it's kind of a good representation, representatives of sampling-based approach. And the performance is evaluated using the IPC score. Actually, the more detailed results or analysis for different algorithms and the IPC can be seen in the organizer's papers. So here I'm just briefly going over the results. So first let's look at the total score over the IPC 2018 problems. So at the bottom, where is the lifted conformance of BOFA, it achieves the IPC score about 90. While the PROS 2014, which is winner of 14 and 18, has achieved about 37. And what we can see for each of the domain is that, first of all, for the red fin blue eye and cooperative recon, which are really large problems with large action space, we perform very well compared to sampling-based approaches. And I want to show here for the manufacturer domain, where you basically build a factory and you want to have a plan of producing and sell and hiring people. So it really requires a good sequence of actions to succeed. Using a conformant extensions, which is bottom two lines, is much better than the middle sessions of the algorithms without a conformant extension. And interestingly, it's also better than the PROST. This is interesting because in this domain, the legal action space are really just a couple. It's very small. So for each of a state, there are only a couple of legal actions to take, which is definitely a good domain for sampling-based approaches. But here we're also outperforming it. This is definitely a good direction to look at and to understand why we perform better than sampling approaches. Likewise, the chromatic is not a big problem, but we also outperform the other planners. We're pretty much similar to the PROST in academic and wildlife, while on the really small problems where the UCT can basically fully expand the tree and find the global optimal solution, it is much better than our algorithm, which is just suboptimal. So this is just a very quick review of the results in terms of action size, but that's definitely, there is more thing to look at. I'm going into the end of the discussion. I probably ran out of time, so I want to leave it to the Q&A session where we can talk about correctness, why should it work, can support other domains, and can we remove the independence assumption, blah, blah. But I think there are a lot of things. Eventually, I want to talk a couple more points about SOPOFA. So SOPOFA has been applied to Bayesian inference algorithm, like marginal problems. And our preliminary results show that it's promising to extend the SOPOFA to MDPs. And also the code and related papers are on GitHub. So it's the best way to understand this algorithm is to find this GitHub code, to find GitHub page. And also you can search over Google the name of the algorithm, SOPOFA, so it should be easily to find it. Okay, pretty much that's it. Thank you for listening.
Hi, thanks. Very interesting. So you were mentioning this equivalence with belief propagation.
Yeah.
So what type of, so belief propagation run on the joint state, and then you have the action, or belief propagation on the factored?
Oh, the factor.
Because in the factor, it might be the case that belief propagation doesn't convert, right? If you have many interdependencies. So what do you mean by equivalence? That
sure, yeah.
The marginal you get is some.
That's a very good question. So actually, what I mean by equivalence is that it's equivalent on this graphical model in a forward concatenated, it's not projecting. But yes, so it's the graphical model that I just showed in previous slides. It's a concatenation of different time steps of DBN representation of the transition. So it's on factor domain for sure. And as you just said, belief propagation is a proximate algorithm, just like our algorithm.
Well, but if you make the joint state, then it's exact.
Yeah, right.
So then it's not just, it's like the optimal, no? It's the optimal value function.
Exactly, but we work on the factored variables, so it's approximate. And I think the only condition for that to be exact in our case is that the graphical model turns out to be a tree, where our correctness statement in this paper is also stand, but it rarely happens in any domains. So,
thanks.
Florian, another question?
So one disadvantage is obviously that you don't have optimality guarantees, right? So do you have an idea how you might want to, or how you could add that to this?
Yeah, so I will relate that question to the previous question. Actually, it's about how we deal with independence assumptions. And the previous question actually mentioned that we can use a mega node, which is saying that, okay, for some of the nodes, we shouldn't deal with independence assumption. We can treat them as not independent. But together, this whole aggregate simulation needs to be extended, and we are sure that the resulting computational graph would be very large. So it becomes a balance. We're talking about one extreme where we assume independence everywhere. But the other extreme is that you can represent the exact value function in a very complicated way where it's infeasible to represent or optimize. But we can definitely do something in the middle. So it depends on, but the question is, in a theoretical view, we can do that to the other extreme, but in practice, we have to decide that in the planning time. So we have to decide whether this is how much independence we can do and how much non-independence we can hold. Yeah, I hope that answers the question. Yeah.
Any other question? No, so this is the end of the session. Thank you very much.
Yeah, thank you.
And if you break now.